Hi everyone. So I am Dr. Erick Chacon Montalvan, and I am a postdoc in the group of data science of the natural environment that is inside the mathematics and statistics department. And today I will provide a presentation about a model-based approach for integrating spatial data, in particular environmental and health data with different supports. So when we talk about spatial data analysis, we have to consider the concept of scale and support. And that is going to depend of three definitions that I'm going to present here. The first one is with respect to the phenomenon under study. Here, this phenomenon is represented with a heat map where the lighter colors have higher values and the darker colors have lower values. You can think of this phenomenon, for example, as the risk of having a disease, or the risk of having a particular health status, or maybe some environmental variables or processes like precipitation and temperature. And in this case, the support for this process is continuous, and because we can observe, like you have observations at any point inside this bigger square. And then the second concept is the sample units. And these sample units are represented by these white squared. And the idea of the sample units are units where we use to obtain some information about the continuous process. Take in consideration that when we obtain some information inside these units, we usually don't have detailed information inside each square, but what we obtain is just a summary of information about the phenomenon inside each square. For example, it can be the mean or the average level and the average level or the total, sorry. And also notice that these sample units have some properties like the size, the shape, and spacing. Okay, so in this second case, the support of the observed data are these white boxes. And then in the third case, we have the support of the analysis of data, which is basically just the support these squares here, where we want to obtain inferences or prediction about this phenomenon under study. So you can see that this is usually what we have to deal when we have spatial data, and we have to understand the support and scale of the phenomenon under study, of the sample unit, and also the analysis of the data. So when I'm going to show two common approaches that practitioners work for those cases. So for example, one case is the same. So we have this phenomenon, we have these sample units, and what they use is that they try to represent, to use a process that is discrete in this support that we have to here, the white boxes, and they take in consideration the association and other characteristics of this process, but using only this sample unit. The disadvantage with this approach is that when we do some inference about the phenomenon under study, we can only make inference in the same support where we have observed the data. So for example, here we have these three squares that are three units about this phenomenon. And then we are going to be able to make inference on those three units, and the same for the remaining squares. So when we use this approach, we are not able to say or to provide more information um, away of these squares. Okay, so the second approach, quite common, is that instead of using the support like these previous white squares, what they use is just centroid of these supports. So for example, I'm representing here just these points, and they assume that information that they have is just about these particular places. The problem with this approach is that you neglect the support, so you neglect the sampling unit and their properties as the size, shape, and spacing. However, at least with this approach, you can perform some continuous inference about this phenomenon under study in any place that you decide here, for example. Of course, the interpretation of those and predictions are going to be limited. So, because of this complexity and because both approaches are not completely adequate, so we provide an approach where we can integrate this spatial health and environmental data for for various applications. So in the following map, you take in consideration that these circle nodes are random processes and the square nodes are observable data. Okay, so we in this approach we first define a continuous latent model, this the green nodes. that try to represent the system that we are understanding. So for example, YS can be, I don't know, maybe the risk of a particular disease, and we have this W1, W2, and W3, three processes that in some way help you to understand this risk. And then in this second level, we represent this, we project each of these latent variables to a new support, which is this news. Now, for example, we have YS here, and we can project this process to a new support, like in this case, and also in this case. And finally, in the third step of this approach, we now can associate this process on the support that we have observed data with the observed data. Okay, so using this approach, we actually can deal with several applications where the data comes from with different supports. And you have to notice here that one important aspect for our approach is that we should be able to represent this continuous process in any type of projection or any other support. And so in the following figure here, I can show you that we have a representation of a, well, we have a mathematical representation, but here with simulations, you can see that on the left side, we have continuous representation or realization of our process. And we have also representations of this process on different supports. In this second example, we have representations on a regular grid. And in the third case, we have representation or realizations on irregular grids, like in this case. So when I say irregular grid, you can see that these intervals are constant over this dimension, while here the intervals are smaller because it represents, for example, a measure that you have in a longer period of time, and then you have a smaller period of time, and here you have a very small period of time, and so on. So those are the supports, and we have realizations of our continuous process on different types of supports. So in theory, this works, and now because we use this representation, now we can use our approach that we defined here before. So let's see an example here. So in the following example, I'm showing two cases. On the left, we have the classical approach where you ignore the support of the spatial data. And on the right, you have the case where you take into account the support of the data. Okay? So in both graphs, you can see that the blue lines represent the continuous process that we want to study. The black intervals represent the support of the observed data, and the red line represent the predicted mean. Okay, so the main difference with both approaches is that, for example, when you ignore the support, what's happening is that you have row changes, like drastic changes on this predicted mean. For example, in this place here, because you have one observation here, there is this strong change here. While in our case, because we consider the support, you can see that there is not such strong changes, it's smoother, the type of prediction that we obtain. And second, uh, remember also that these gray lines represent, help us to understand the uncertainty of our predictions. So if there is a bigger range of these values, you can see that there is higher uncertainty. If there is a smaller, there is lower uncertainty. So you can see, for example, here, when you ignore the support, there is this strong fluctuations of this uncertainty. While in our case, when we don't ignore the support, there is not such a strong fluctuation on this uncertainty, and that can lead you to overestimation or underestimation of the uncertainty. For example, in this case, when you ignore the support, there is an underestimation of the uncertainty, and that can lead you to biases on the prediction, like in this case, in the continuous process. While here you can see that our uncertainty takes into consideration the continuous process. It means that our process or our approach explains better the phenomenon under study. So for example, in the following figure here on the left, it's another way to see the fluctuation of the variation. Like for example, when you ignore the support is the blue line, and you can see how this blue line has a strong fluctuation to the point that it can go to zero, very close to zero, and then can jump. While our approach doesn't consider that, when we consider the support, you can see that there is not such changes that go close to zero. And why this is important? Because this can, if you use a, let's say, a non-adequate approach, that can lead you to erroneous decisions. So imagine that we are interested in computing the exceedance probability. In this case, the probability that the risk of having this disease is, the additional risk is greater than 1.25. So in this case, you can see that around this axis level or x-axis level, you can see that with our approach, this probability is greater than 0.5. And with the other approach, when you ignore the support, this is much lower than 0.5. So this means that, for example, when you take a decision, these two approaches are going to lead you to different decisions. And in this case, probably what the decision that is wrong is this decision that is led by this non-adequate approach, which is when you ignore the support. So this is just a way to explain how important it is to model spatial data, taking in consideration the support of this data. And this is a work that we are doing in collaboration with some colleagues in the math department. And and yeah, and that's all. I don't know if there is any question. Thank you.